So 3.4, solving some logarithm and exponential equations. Hopefully this is one of the lighter lessons, so if everything's been making sense so far, this should just kind of recap a few things. So the first thing I want to remind you about is that natural log, or LN abbreviation, is the same thing as log base E, because the E shows up so much in the natural world with a lot of applications that it has its own designation. It's that important. So whenever you see natural log, just remember it's log base E. Now I'll help you with this first example, where I'm going to ask you to solve for x. It's e to the 2x plus 1 equals 10. So you could think about rewriting it as a logarithm, or you could think about taking the log of both sides. So I'm going to show you both, and I'm also going to write that log base e for this one, but I won't keep doing that. I just want to make sure that I really drive that point home. So option 1 is to just flat out rewrite this thing. Since it's e to an exponent equals 10, we can say log base e of 10 is 2x plus 1. And log base e is natural log, so log of 10 is 2x plus 1. And what I'm going to do here is give an exact solution. That's always acceptable on a test or a quiz. If I tell you you're allowed to round to 2 or 3 decimal places, then you can always put this in the calculator. But sometimes I will expect you to do this by hand so I can see that you can do all the algebra. And from here, it's just some algebra 1 stuff. Subtract 1, and then ultimately divide by 2. And that would be your final result right there. Natural log 10 minus 1, all that divided by 2. Most people tend to go with this option. Option 2 is to take the log of both sides. So knowing that it's log base e, and I can do whatever I want as long as I do it to both sides. This could be a little cramped, but I'm taking log base e, or natural log of both sides. What that's going to do, if it's base e of e, that goes away, and all you're left with is 2x plus 1. And then over here, you're taking log base e of 10, so you have natural log of 10. And that takes us right back to this point. So from there, the work will be exactly the same. It's up to you. Whatever process makes more sense to you that you prefer, I really don't care as long as you get the job done. So the second example here is to evaluate something that's not real straightforward. It's a fraction to a power, which is a little strange, to figure out what it equals. So we're going to solve for x. Again, the whole point of an exponent, or the whole point of a logarithm, is when your variable is an exponent, and you're trying to find that. So you take a logarithm to undo this exponential process. So if you recognize that 27 and 81 both have a base of 3, then that's going to tell you, or give you a big hint, that log base 3 is probably going to show up in here somewhere. Now, if you don't see that right away, that's okay. What I would recommend to you is, since the x is an exponent, and that tells you you're going to need to do a logarithm to solve for x, the base you're going to choose is going to be really important. So that should be something you're kind of thinking about. But again, if you're not sure that 3 is the base, you can't just glance at this and spot that. That's okay. What you can do is take 27 and 81 and break them into prime factors. 27 is going to be 9 times 3, which is going to be 3 cubed ultimately. 81 would be 9 times 9, which would break into 4 threes. So 81 is 3 to the 4th. So hopefully, once you do that, it's pretty obvious to see that these are both base 3. 3 cubed is 27, 3 to the 4th is 81. So knowing that, and I can do whatever I want as long as I do it to both sides. So I'm going to take log base 3 of both sides, because both of these numbers are, or can be written in base 3. If you're unfamiliar with what that means to write a number in a base system, we live in base 10. You have the ones place, the tens place, the hundreds. So 10 to the 0 is 1. 10 to the first is 10. 10 squared is 100. 10 cubes is 1,000. Maybe one day we'll have a little bit more, talk a little more about bases and some of that stuff with the problem of the week. So I'll leave it at that for now. So we're going to do log base 3 of 1 over 27 to the x, and log base 3 of 81. So log base 3 of 1 over 27. Well, for that, I would recommend that we rewrite 1 over 27. If we know that 27 is 3 cubed, then 1 over 27 is 1 over 3 cubed. And that can be rewritten as 3 to the negative 3. So 1 over 27 is 3 to the negative 3 power. And of course, all that was still raised to the x. And that's going to equal log base 3 of, and I'll do the same thing for 81. 81 is 3 to the 4th. So if it wasn't immediately clear why I would want to do log base 3 of 3 to some power, what's going to happen now is these can cancel out, basically. It's by that rule we've talked about, but we know that at this point that's something we can do. They can basically go away and 4 is all that's left. So that side's a little easier. I'm going to start with that. I'm going to come back over here. So at this stage, I've got 3 to the negative 3, but then it's to the x also. When something gets raised to an exponent, the 3 is going to get raised to that power, but the exponents can be multiplied. So let's go ahead and rewrite it that way. So 3 to the negative 3x. Because again, if you have something raised to a power, the exponents multiplied together. That's your exponent rules. And we get the same situation where it's log base 3 of 3. So negative 3x is all that's left on this side now. 4 is all that's left over here. So negative 4/3 would be your final result. And you can always plug it back in the calculator, and I recommend you do that. Plug that back in here for x and verify that it does come out to be 81. Example 3 is probably the easiest one on the whole page, as long as you understand what we're doing with the logarithms. Because it's 4 to a power equals this, we can just rewrite it as a logarithm. The base would be 4. 246 is what we're taking the log of, and that would be your result. So in your calculator, and I've already got it, but I'll show you the steps one more time. It's alpha window. We choose number 5 versus log base. Log base 4 of 246. And there you go. So that's all you got to do, 3.971. And that would be your answer. All right, example 4 is going to pull in a couple ideas. Domain's been a big thing all year, and that's going to continue to be a big thing all the way through calculus. So we're going to really have to keep focusing on domain with a lot of problems throughout the year. And I'm going to forget that I said that for a few minutes until the very end here. So let's just kind of run through what we could do. We have natural log of x plus 6. There's really nothing to do there. But on this side, the two natural logs are subtracted. So let me revisit some rules here. A natural, or any log, is an exponent. Now, if exponents were subtracted, then the other numbers you were dealing with had to have been divided. So that means, from your rule, that these bigger numbers, if you will, the x and the x plus 2, they had to have been divided. If those were getting divided, then any exponents they had would have been subtracted. And that's, the logarithms are exponents. So that's why that quotient rule works the way it does. And now, because you have natural log on both sides, these pieces have to be equal to balance the equation. So x plus 6 would equal x over x plus 2. And to solve, we need to get rid of the fraction. So I'm going to multiply by x plus 2 on both sides. So now over here we have x squared plus 6x plus 2x is plus 8x and plus 12 equals x. And then to finish solving, we can set this equal to 0. So subtract this x out. So x squared plus 7x plus 12 would be 0. And if you need to do some other stuff to factor, that's fine. But two factors of 12 that add up to 7 are 4 and 3. So x plus 4 and x plus 3 would factor this down. And that tells me that x equals negative 4 and x equals negative 3 should be solutions. Now, we definitely want to check, and here's where that domain comes in. So I'm going to flip over to the graph for a minute and give you a visual of what will and will not work here. And then we'll come back and talk about how we could have done that without a calculator. So now I've got my two equations loaded up. Basically, left side, right side is two separate equations in Desmos, so you can do this in the calculator. When you do that, you're basically creating a system, and you want to see where they cross one another. That'll be your solution. So let's look at them separately. There's log of x plus 6. There's log of x minus log of x plus 2. So all we got to do is figure out where they cross. That's kind of a problem. They don't. All right, now, if you're if you're solely going by a graph, you might spend a lot of time chasing that thing down. Whereas if you just use the domain in the beginning without a calculator, you probably would have gotten done a lot quicker. So these aren't going to cross. So there's no solution. But let's try to figure out how we could have known that without graphing. So here is the parabola that I solved. When I solved for x, I got those two solutions of -4 and -3. And really the parabola is not important. What's important is if this thing was going to have solutions, they would have happened at -3 and -4. The problem is one of these doesn't exist at those points. And this is where domain comes in and why it's so important. So for this, the right half of the equation, log x minus log x plus 2, we'll check the domain separately here in a moment, but there's no way you could ever plug in a value smaller than 0 and have it work on that side of the equation. And since the only two things that could have been solutions don't work when you plug it in, this problem has no solution. So at this stage, in the very beginning, let's just look at what is possible and what we can't do. So I'm going to look at the log of x for an example here. So log of x, let's say it equals y. We could rewrite that as e to the y equals x. Well, let's think about some possibilities. So I can plug in a positive number for y, and I get a really big number for x. Okay, so like put in e cubed, or e to the 4th, or e to the 10th, e to the 100th. X will just keep getting bigger and bigger and bigger. Okay, so if I plugged in, say, 0 for y, then x would be 1. And if I plugged in a negative number for y, so let's say like -2, well, x is going to be something, it's going to be 1 over something that's getting pretty big. And if you keep plugging in bigger negative numbers, like I plugged in e to the -100, well, this would be 1 over e to the 100. That's going to get really close to 0. So if you think about an exponential, they had a horizontal asymptote at 0, because no matter what we plug in here as the exponent, our result is never going to quite make it to 0. It's going to get close, but it's never quite going to get there. And since a logarithm is the inverse of an exponential, then we can never take the log of 0, because this is the result we're going to get out. And by that logic, you'll never get a result of 0 or a negative number for that matter. Graphically, if for an exponential y equals 0 is the horizontal asymptote, then on the inverse x equals 0 would be the vertical asymptote. You'd never have a value less than 0 or equal to 0. So that's kind of a quick explanation of why that's the case. But for your domains, since what's inside of here cannot be equal to or less than 0, x plus 6 has got to be greater than 0. So that tells me that x has to be bigger than -6 for the domain. For this part, x would have to be bigger than 0. For this part, x would have to be bigger than -2. I'm just saying that what's inside of here cannot be 0 or negative. So whatever's inside of here has to be positive. That's how you check. So you just say x plus 6 is bigger than 0, and see what it comes out to tell you. And if you put all these domains together, think of them like and statements. It's got to fit this case, and this one, and this one. If you put them all together as an and statement, the only thing that overlaps is the x is greater than 0. So that tells me that whatever solutions I get, they have to be bigger than 0. So let me just kind of run through that real quick. If we did a number line, here's -6, here's 0, here's a -2. So you'd have an open circle going right, open circle here going right, open circle here going right. The only thing that they all would share would be everything from 0 and greater. So your overall domain, it has to be x values that are bigger than 0. So when you get to the end and your two solutions or possible solutions are both negative, neither one can actually work. So there's no solution to this problem.